In this experiment, you will be measuring the value of the equilibrium constant of a reaction. And so to introduce the concepts, we'll talk first about what equilibrium is for a moment. Just in case this has not been covered in your lecture course yet, or just as a refresher to reframe our thinking in the context of this experiment. So what is equilibrium? If we have a reaction, which we will in this lab, have a reaction between iron and thiocyanate ions, which is shown to the right here, we could expect that there's likely some product if this is a reaction, correct? And the product that we would actually form here would be a complex, which we'll learn later in the semester what a complex is, but a complex between iron and thiocyanate, and this would be the charge of that overall species if it's a 1-to-1 ratio forming that complex. Okay, so this is the product of that reaction, FeSCN2+. Now, we tend to assume that reactions go forward in the way that they're written, and this has been how we have seen reactions up until this point, but reactions often do not just 100% of reactants turn into products. Oftentimes, there is some point in the middle where the reaction will kind of just stop because it doesn't have the necessary energy to continue making more product. It finds a place of balance, and we'll kind of discuss what we mean by that state of balance. The better word for that is equilibrium. So in reality, some of the product that we are forming actually gets converted back into the reactants. And so we can actually write the reverse reaction because this also has some relevance at the same time, the complex breaking apart to form the ions. So both of these reactions are happening at the same time. And the way that we would typically write a reaction that this is true of, which is true of a lot of different reactions, is that we would write it with these reversible arrows, and we'll write it in the way that we like to think about it, reactants forming products. But the reversible arrows imply that both reactions are happening at the same time, forward and reverse. All right, so you may have seen these double-headed arrows before, but this will tell us it's a reversible reaction, and that also means that it will reach a state of equilibrium. All right, so if we think about the forward reaction only, at initial time, we have high concentrations of Fe3+ and SCN because they should be the only things there if that's what we mix together in our solution. And so I'm going to start from a point up here, and we'll just assume that's the concentration of our FeSCN. Over time, this concentration of reactants should go down because we're expecting that some of this forward reaction will occur. At that same time, we already said FeSCN2+, the product complex, should have started at 0 because we didn't put it in our original mixture. So over that same course of time, as some of our Fe and SCN ions are reacting to form product, we're seeing that product start to appear. So that's what that little initial line is there to represent. Eventually, and as I already mentioned, the reverse reaction is going on at the same time. That will actually cause the increase in the FeSCN product to go down, so that rate of increase won't be as high because it's breaking back into the ions. And so that also causes a corresponding decrease in slope for the reactants concentrations decreasing. And they'll reach a point where both reactants and products sort of level off in their overall concentrations. And that is because we've reached a state where the forward and the reverse rates of the reactions have become equal. So just as many events in the forward reaction are occurring as events in the reverse reaction, and so the concentrations don't really change anymore over time. They've essentially leveled off. That average concentration is very stable at that point. So that leveling off point is what we would label to be equilibrium. All right. From there, we can write an expression that will actually allow us to calculate a constant that describes that equilibrium. And we usually just call it K, but we're calling it Kc here to be a bit more proper. Kc refers to a concentration-based equilibrium constant, but K is the equilibrium constant. I'll just say eq for equilibrium constant. All right, EQ. So the value of the equilibrium constant can be determined based on equilibrium concentrations of product over reactants. So the product being Fe SCN 2 plus over each of our reactants, Fe 3 plus and SCN minus. This is the formal expression. When we actually have values, we can plug them in and calculate a value for the equilibrium constant. And that is actually the goal of this experiment, to obtain measured concentration values at equilibrium so that we can calculate an equilibrium constant. So let's talk about how that will be done. All right, in this experiment, I've kind of used colors to try to illustrate this, but the initial reactants are not going to have a real strong visible color, so I've been labeling those in gray. But so if we put in our iron and our thiocyanate into a test tube, initially we might see kind of a clear solution, but after a certain amount of time, we will get a reddish orange colored solution. And so that is what is represented by the second test tube here. As you might recall, when something is colored, we can easily measure its absorption in the visible wavelength range. And so we have a detectable absorption spectrum for the product. And using the Beer-Lambert law, we can actually relate the absorbance of the solution to the concentration that is present in that solution of that substance. And we do that by way of measuring first its molar absorptivity coefficient. And so if you look to this formula here, we have the absorbance of the solution is equal to the molar absorptivity coefficient of that compound or complex, and times the path length, which is the distance of the cuvette, and we use 1 centimeter cuvettes all the time, so we basically just plug in 1 here, which makes it irrelevant to the calculation overall. And that then multiplied by the concentration of that species in solution. Now, when we're first trying to figure out, how to characterize our substance, we will set values of concentration so that we can figure out the relationship between concentration and absorbance by way of getting a number for the molar absorptivity coefficient. Once we have done that, or gotten our Beer's law plot, and we know our molar absorptivity coefficient, then we can go about measuring absorbance and calculating concentration based on that. So this first step is a step of calibration. We're trying to calibrate how much absorbance we should get for a set amount of concentration of this particular species. And so the strategy is to say I made a 1 millimolar solution, and a 2 millimolar solution, and a 3 millimolar solution, and a 4 millimolar solution. I would measure absorbances of all of those solutions, put them on a plot, absorbance versus concentration, and then get a best fit line for that plot where y is equal to my absorbance, my x value is my concentration because these are my axes, and that must mean that the coefficient of x is our molar absorptivity coefficient, because remember our path length is just 1, so we can ignore it. So m in the y equals mx plus b must be our molar absorptivity coefficient. So that's why I've labeled it with epsilon here. The b term is an error term, and you can account for that in your measurements if you would so please, but sometimes people just ignore that. It depends on the context of what you're doing, how detailed and precise you want your measurements to be. Okay, so we've got our Beer's law plot. We've extracted a molar absorptivity coefficient. This whole process we are going to be going through in part A of the lab, because we're just going to assume we don't know anything about FeSCN2+, and so we don't know what the molar absorptivity coefficient is without measuring it. So that's step 1. In the second part of the lab, we're going to work on actually measuring the value of K for the overall reaction, because now we know the relationship between concentration and absorbance. So our strategy is, okay, now we're able to measure the concentration of a reaction component, and that reaction component would be the product at equilibrium. We're also able to prepare solutions with initial known reactant concentrations, because, you know, when you mix them together in your test tube, you know what concentration you put in there if you measured it precisely. So because we know the initial concentrations of reactants and we know the final concentration of product, we can deduce how much reactant must have turned into product using an ice table method, which hopefully was covered already in your lecture class, but if it was not, this is another great way to learn it. So the ice table method is essentially you write out a table where you have an initial line, a change line, and an equilibrium line. You write the reaction above the table so that you can, for each line, represent each species concentration. And so on your initial line, when you mixed things together in your test tube, you know how much iron 3+ concentration-wise you're putting into that test tube. Same thing is true about the other reactant, the thiocyanate ion. So you can plug in those values into your table. You know that you did not dissolve any product initially, so you can put that value as 0. So let's ignore our change line for now, because in this context where we don't know K, we're actually not going to write anything on the change line initially. The equilibrium line is our other measurement. So, we set up these based on our precise measurements of concentrations initially, and we measured the reddish-orange absorption concentration based on our Beer's law plot. We calculated an actual molarity value of our product. So if initially we had 0 product and now we have a measured concentration of product, the change from initial to equilibrium must have been the difference between 0 and the final concentration. That difference, because this is a 1-to-1 molar ratio, must be equal to the difference in initial reactant concentrations. So I could just say iron 3+ minus the difference we measured for our product, and same thing for the thiocyanate. So let's just say, for example, I made, just to give us a number to put here, let's say I made 0.0003 molar FeSCN at equilibrium. That value minus 0 is the number I'm going to plug in for my difference. And so I would subtract the initial concentration minus that difference to get the equilibrium concentrations of reactants on that final line. All right, so I would take these values that I have on my equilibrium line and plug them in to my equilibrium expression. Now that I actually have equilibrium values, I can set them up to solve for K, my equilibrium constant. So divide equilibrium measured concentration of FeSCN2+ divided by the calculated concentrations of reactants at equilibrium based on our initial and final measurements. And once we've done that, we have a value for K that should tell us essentially where the equilibrium lies for this reaction. But you don't ever really want to do anything in the chemistry lab where you're just making one measurement for something that should be a constant. We're going to make multiple different measurements, and we're going to vary our initial concentrations. And one of our research questions will be, is the value of the equilibrium constant? Is Kc constant? And if it is, how is our accuracy going to be improved by our use of multiple trials? So I would keep both of those things in mind. And hopefully we can obtain really robust values for our equilibrium constants.